Welcome, everyone, to our fourth presentation in the Osher Lifelong Learning Institute 2026 at the U Lecture Series. I'm Laura Peterson, an OLLI volunteer. The Osher Lifelong Learning Institute at the University of Minnesota is a vibrant learning community for people aged 50 plus. Part of the College of Continuing and Professional Studies, OLLI belongs to a national network of Osher Lifelong Learning Institutes supported by the Bernard Osher Foundation. I would like to acknowledge and say thank you to our sponsor, the University of Minnesota Alumni Association. We also acknowledge that the University of Minnesota Twin Cities is built within the traditional homelands of the Dakota people. It's important to acknowledge the peoples on whose land we live, learn, and work as we seek to improve and strengthen our relations with our tribal nations. Today's presentation is Exploring Antarctica's Future and World Sea Level Rise by Ice Coring into the Past with Dr. Peter Neff. Dr. Neff is an assistant professor in the University of Minnesota's Department of Soil, Water, and Climate, a glaciologist, and a climate scientist working primarily to develop glacier ice core records of past climate, environmental conditions, and atmospheric chemistry. Dr. Neff's current research focuses on better understanding recent climate changes in coastal regions in West Antarctica, areas which play a large role in uncertainty for future projections of sea level rise. Dr. Neff is also working to capture the last 200 to 500 years of hydroclimate variability in southwestern British Columbia through recovering and developing the southernmost annually resolved ice core record in North America from Mount Waddington in the Coast Mountains. Dr. Neff is also the Director of Field Research and Data for the Center for Oldest Ice Exploration, a National Science Foundation science and technology center that seeks to find the oldest possible ice core records of past climate preserved in Antarctica. I will turn this over to you, Dr. Neff.
Thank you so much, Laura. I hope everybody can hear me. Thank you for joining. And I see a great number approaching 200 participants there. So, yeah, hopefully I hit the mark and can give you an exciting overview of the work we do in Antarctica through studying glacier ice and the layers of information preserved in it. Help us understand how Earth's climate system has worked in the past and how it will work, how it might work going forward. So I'll just say that, yeah, I can't see the chat while I'm presenting, so I'll leave it to others to interject any burning questions if need be. Let's see here. I'm going to make sure I have my setup so that I can see my video preview. So just give me 1 second. And here we go. Okay, that's better. Yeah, so I sort of have a couple different buckets that I want to make sure that I address here. But yeah, first of all, I'll introduce myself. I'm Peter Neff. I'm an assistant professor over on the St. Paul campus of the Twin Cities here at the U. So I'm in the College of Food, Ag, and Natural Resource Sciences over on the farm. I'll be talking, sort of framing this around the most recent work that I've done in Antarctica with support from the National Science Foundation and also the Korea Polar Research Institute with this fine icebreaking research vessel they have that allowed us to accomplish so far my dream project in my career and what we're continuing to work on right now to learn from and tell us about recent climate in a critical part of Antarctica that I'll hopefully teach you about here in the next 45, 50 minutes. And so the sort of science title of that is that we co-led this U.S. South Korean expedition to recover the first 20th century long or almost 20th century long climate records near Antarctica's most remote and concerning glacier for future sea level rise. So it's a really hard place to get to. We managed to go there just over 2 years ago, and that'll sort of be our trip to Antarctica by the end of this. But my list of major things to take away in case you fall asleep or need to take a lunch break while I'm talking is that Antarctic ice cores, I'll share with you, give us our sort of highest fidelity, highest quality records of past climate, including records of atmospheric composition, those important greenhouse gases, particularly that keep Earth at a nice habitable temperature, but are increasingly warming us as we emit more greenhouse gases. You'll learn about West Antarctica, which is a central uncertainty in our global projections of sea level rise. I'll add my contribution of how our new ice cores will hopefully help us advance our understanding of the most important glacier in the world, but certainly Antarctica. It's called Thwaites Glacier. And then underneath all of this, I want to give you a sense of how Americans do research in Antarctica through the National Science Foundation and the United States Antarctic program that is operated by NSF. And if you are convinced that this work seems valuable and certainly it's a pipeline for folks like me getting into STEM research, I'd encourage you to continue supporting stable funding for the National Science Foundation and other science agencies like NASA. Um, let's get into sort of why I'm here and where we are, right? I'm sure, scattered about the metro area and beyond in this OLLI community. But here on campus, right, we're living on the edge of a former ice sheet in the Twin Cities and across much of the mid latitudes of North America. I grew up in Washington State, where it's very similar, evidence of past glaciers on the landscape, and those are no longer there due to the tiny changes in Earth's orbit around the sun over hundreds and thousands of years change climate enough to make for an ice sheet over Canada or not, right? We don't have one anymore, and that's because our orbit with respect to the sun has changed slightly, and we have a different conditions going on right now with our human activities that are adding heat to the Earth system in different ways, and that are being even more so problematic for ice on Earth, which is somehow my topic of study. And really the reason why ice is my topic of study is because of how I came to my state university. In the case of me, it was University of Washington, through our public school system there, and I encountered National Science Foundation funded research there, and I've continued ever since, discovering actually as a sophomore undergraduate this type of research in the polar regions. And so I'm a huge advocate for the continuation of our longstanding federal university research partnership, where scientists, professors, students, graduate students at universities do a whole lot of research on behalf of the American public, funded by agencies like the National Science Foundation, whose only job is to allocate the funding that Congress tells it to university communities across the country, where not only scientists are doing this research, but our entire university communities across all job sectors, making that sort of heart of a part of the Twin Cities economy and the state economy. So um, that's why I am here, and that's why I've also gone from this slightly mad-looking young scientist working on a deep ice core, actually the deepest ice core that we've ever drilled as Americans in Antarctica, back in 2010, through sort of 14 years of additional U.S. federally funded and international Antarctic research projects, sort of led me to being in the position in January 2024 to accomplishing this first sort of big dream project with my partners in South Korea and other international partners that I'll teach you about. And ice core science has been my central um, topic of study. So we should talk about Antarctic ice cores for a bit. Um, my pitch slide for ice cores here, which is going to zoom in and out on a piece of glacier ice from 100 meters below the snow surface that you see here in this image. It's from a place called Law Dome in Antarctica. But ice cores really let us explore climate processes, trends, and extremes in places or at times where we wouldn't otherwise have observations, because the layers of snow and ice, particularly in the polar regions or at high altitudes, never melts. And so we have a continuous stratigraphic record of chemical information preserved in that snow, and also air bubbles trapped by that snow as it's compressed into ice, as you can see here in this image. And so having that extra information in space or in time gives us perspective on climate, environmental, glacier, and ice sheet sensitivity, especially on this warming world that we understand right now. So that's sort of the sensitivity of those systems is sort of the unifying term there. We're all trying to understand how sensitive Earth systems are in this changing world. So I wish you could all be with me here on campus. I have a prop with me. I actually can't see my video still here, but I have a piece of an Antarctic ice core, which is going to drip all over my keyboard. But you can see the air bubbles inside it. Any glacier ice has those air bubbles, which formed as that porous air space between the fingers of snowflakes, and that is our archive of past air, in addition to the chemical information in snow. So Really fundamentally beautiful, clean archives of past um, information that we recover, particularly from Antarctica. I'm just putting away my prop here. Um, because of how clean the snow is in Antarctica due to that continent's distance from any other continent and any other source of dust, besides maybe the few mountains or the few outcrops of rocks that do exist in Antarctica, which are very few and far between. Ice core science is sort of a long, slow business. So we have to go from recovering our ice cores there on the left, drilling them in the field, and then bringing back hundreds, if not thousands of pounds of ice to labs where we then sample them. We cut them into smaller pieces to get the cleanest intersections of the ice, which we then put on chemical sampling instruments like on the right, which is actually a heated melt head that we use to melt the cores and instantly plumb that melt water into a range of instruments to measure the chemistry of the snow and ice. And actually, simultaneously now, we can measure the concentration of greenhouse gases in that ice. So I want to make sure you sort of see the chemical information that we're working with here. I know this is a lot of wiggles, but we still got that ice melting on the right. And so that, imagine that stream of meltwater going right into laser spectroscopes, ion chromatographs, mass spectrometers to measure all these different parameters that you can see with the vertical gray bars here. This is about a 7-meter section in the top part of an ice core that I worked on many years ago. The top are water isotopes, how hydrogen and oxygen molecules are slightly varying in mass is an estimate of temperature. You can see sulfur compounds in oranges and purples there. Sulfur in the Antarctic environment is seasonal due to how the ocean freezes over and eliminates sulfur emissions from the ocean in the wintertime, but in the summertime, as the ocean melts, ocean surface melts, it emits sulfur. So these are all of our annual markers that let us count layers of time back in time. And actually, at places where it snows enough every year, you can count these layers back in time up to 30,000, 40,000 years ago before we then have to use other methods to date older, deeper ice cores. Uh, the international community has drilled ice cores at a range of places across Antarctica. So we'll sort of slowly get to know Antarctica here. I'll try to always have the reference map on the top right there so you can place Antarctica with respect to some other continents. It's too often by itself there. So we've got decent coverage across Antarctica. These are deep ice cores that were drilled to bedrock at various depths in Antarctica. And we have particular conditions that we need for interpretable layers in the ice sheet that we would go to drill an ice core. And that tends to be what we call them domes, ice domes. So the entire ice sheet itself is sort of like a dome, where the central part of it is like being at the top of a watershed or a mountain range. And we like to drill right on top of that, where the layers are accumulating directly in a continuous stack of snow and ice that fell from the sky right at that location. And I'm sort of the odd person who's actually pushing us out to the edge of the Antarctic ice sheet to where we actually have miniature versions of the big Antarctic ice sheet. We have these little coastal domes, coastal ice rises, we call them, that are my feature of obsession in my career through the quirks of the projects and the places I've gone to in Antarctica over the years. And so you'll all be a couple hundred more experts in Antarctic ice rises here in the next 35 or 40 minutes or so, I hope. And so by the end of this, we'll have gone out to my site there on the left, near the most concerning glacier in Antarctica, and in the more challenging coastal regions with respect to their weather. It's quite stormy on the coast, and it snows quite a lot compared to the inland parts of Antarctica, which are actually a polar desert. But the change we see in Antarctica that's contributing to sea level rise and that concerns us greatly for sea level rise going forward, that change is being initiated from the coast inland. It's forced by the ocean currently. And so us not having climate records there, and I'll show you, we really don't on that particular coastline, is a problem that I've been trying to contribute to and get my community to increasingly address. So to summarize ice cores, these are our records of regional to global climate and environmental processes wherever we can get them. Obviously, with ice cores, we're restricted to the Arctic or the Antarctic or the highest mountain glaciers sort of scattered all around the world. But in Antarctica particularly, Antarctica is where we are the only place on Earth where we have a clean archive of carbon dioxide in the past atmosphere, CO2 being the most important long-lasting heat-trapping greenhouse gas in the atmosphere that we're continually adding through our burning of fossil fuels. And our resolution for the information in Antarctica is yearly back thousands of years, if not tens of thousands of years, at places where it snows enough every year. We have continuous records, deep ice cores that go back 1.2 million years. Actually, those are new results just in the last month or so here from our European colleagues. And then I'll show you in just a second here. We actually, through the NSF Coldex project, are getting the oldest ice ever discovered on Earth that doesn't give us continuous information from today back 6 million years, but gives us snapshots of old, sort of stranded, uh, certainly weird ice, I would call it, but dating well beyond the archive of information that we've had until the last few years here. And that's what these look like this. Let's see, I need to get my background there. So we just published this, a group of us from the NSF Coldex project back in last fall in the Proceedings of the National Academy of Sciences. And this paper was just demonstrating how old the ice is we have in Antarctica. And actually, this has a University of Minnesota connection beyond myself being a part of it, in that the way that we date this very old ice, which doesn't have annual layers that we can count through the chemical stratigraphy, is that we use the argon 40 isotopic composition of the air bubbles in the ice. Argon 40 not only was discovered here at the University of Minnesota by Al Neer in the physics department back in the 1930s and 40s, he also discovered that Earth's crust was continuously off-gassing argon 40 as it decayed from potassium in Earth's crust, a very abundant element in Earth's crust. And because it's continuously adding argon 40 to the atmosphere, we can use it as a geologic clock. So if you have an air bubble that has more argon 40 in it, you know it's younger than an air bubble that has less argon 40. That's the older air bubble. And that's how we date this, this ice core here. So really amazing to look at. You can see the cores from the deepest parts of these boreholes. These are not actually deep boreholes. We go to a place where it's very easy to find this old ice in stranded pockets near the surface. But because it's near rock, the cores are dirty, and that can affect the preservation of some of the greenhouse gases. So these are challenging archives to work with, but because they're so old, the NSF Coldex project has focused a lot on this. And I'll just give a second for these beautiful archives. These are two photos from our NSF ice core facility where we store all of our ice cores, many of our ice cores, at a USGS and National Science Foundation facility in Denver. Really beautiful to look at, and fantastic information coming out of these. I'll be talking about much younger information, but we'll transition to younger information by looking at the continuous 800,000 year record of Antarctic CO2 from the Antarctic deep ice core record here, and we'll do it in just one animation here. So we'll cram a lot of information into this one animation. So our understanding of why Earth is warming currently is connected to our observations of increasing carbon dioxide in the atmosphere. This is our observational record since the 1950s, when we realized concentrations were increasing due to our activities. This stitches it on to the most recent Antarctic ice cores that have CO2 concentrations going back to the Industrial Revolution. And then this is our deepest, longest 800,000 year time series of the variation in CO2 from 800,000 years ago on the left to today on the right. And actually, this is now 7 years out of date already. And so we've already gotten up to about 430 parts per million of CO2 in the atmosphere, which is, as you can see, much higher than any of the past warm periods. We're in a warm period today where there's less ice in the polar regions. But in the past, these warm periods have always been around 300 parts per million or less. And so we understand, we expect, as we continue to add CO2 to the atmosphere, that adds sort of more and more insulation to the insulating greenhouse gas blanket that we rely on Earth for a habitable temperature. And it's just causing our temperature to tick up and up and up. And so that's our observations. If we look at our global observations from temperature, human records of temperature going back to 1850, this is what we have. So we know Antarctica is existing on a warming world. This is the global average. It is more complicated when you look at different regions, but this is actually put together by an independent group called Berkeley Earth that were skeptical of all of these international compilations of temperature records, and independently, transparently reproduced the records themselves. And they found really good agreement between their reconstruction and all these different colored spaghettis are different international compilations of the global temperature archive, showing clear warming in certainly the latter half of the 20th century into the 21st. And we understand very well why this is happening, including why there are wiggles on these curves. And that's because there are all sorts of natural and human processes happening on Earth at any one time. But on the left there, this is their nice breakdown from their annual reports of the different contributors to global temperature warming or cooling over the last decade. And you can see on the left, the largest on the warming side is emissions of CO2 and methane and other heat trapping greenhouse gases. So I say luckily here that we understand very well why Earth is warming, right? It would be great if Earth was not observed to be warming, but it'd be really puzzling if we didn't know why. And so we at least know why Earth is warming. It's due to our emissions of heat trapping greenhouse gases. And so we're all trying to understand both how to limit that warming going forward and also then anticipate how the rest of the Earth system is going to respond to that extra trapping of heat on Earth. So that's sort of the context that our work exists in. Um, and I hope we can resolve any questions afterwards. But so that's sort of my quick overview of Antarctic ice cores and why we're interested in having that archive in the context of a warming world. And I want to sort of add now, thinking of just like how we do research in Antarctica, what our US infrastructure is for Antarctic research, and then looking to why we're worried about Antarctic sea level rise on that warming Earth that I just described. Um, so let's see. Well, let's look back to Antarctica. So actually, this great map, this is our highest resolution digital elevation model of Antarctica, and it's in part produced by a group that you wouldn't know is here, but here on the St. Paul campus in the old livestock pavilion is the Polar Geospatial Center, which is an NSF-funded center that provides the satellite operational and research support for the National Science Foundation Office of Polar Programs. This is a fantastic product, just amazing resolution. So Antarctica is a very large place, right? There's room for the lower 48 United States and Mexico. It's more than 2 miles thick in places, right? Back in the 1950s when we started science in Antarctica and initiated tractor traverses and surveys all across the continent to figure out how thick it was. We didn't know if it was rock covered by a thin veneer of ice or the opposite. And it turns out the opposite is true. And it's very important to be able to quantify the volume of Antarctic ice so that we can understand its impact on global sea levels. And we've done that in addition to having other geologic archives of past sea level change that give us a sense of how much ice, how much sea level rise Antarctica can cause in the past. We've observed its thickness well enough that we can calculate the volume of Antarctica, which is an important variable to have here. But just trying to convey some basics of the continent. It's so large that if all of it melted, which it's not going to immediately, but if it did, it would raise global sea levels by almost 60 meters or 170 feet. Compare that to the size of the Greenland ice sheet, which we've all had entered into our consciousness a bit more in the last few months. Greenland is only about 6 or 7 meters of global sea level equivalent. So it's much smaller than the Antarctic ice sheet. It's more responsive. It's more certain to be melting in the future. But Antarctica is a very large reservoir of fresh water. And so if it starts changing in meaningful ways rapidly, it'll have a large impact on sea level rise. Just another local connection here. One of the ways we survey Antarctica to measure its thickness is using radar instruments on this aircraft. This is a Canadian bush plane, but it's a DC-3, which have been flying for close to 90 years now. This aircraft was built during the Second World War. And these aircraft are refitted actually in Oshkosh, Wisconsin, completely rebuilding them with modern components, modern engines, and they're incredibly capable in Antarctica that our Canadian colleagues operate in for us. But and part of the Coldex project, actually, we did 2 seasons of airborne surveys looking for old ice sites. And you can see the imagery on the bottom. That's the Antarctic ice sheet with its layers, and then a bright reflection on the bottom. That's bedrock, sort of mountain ranges underneath the ice sheet. We mapped for a new part of Antarctica that was only sparsely mapped in the past. So big international interdisciplinary collaborations here. The radar technology on this aircraft from our colleagues from the Coldex project is also part of the radar components on NASA missions to Europa. So our technology and science motivation sort of span across all sorts of disciplines and are headed out to the edge of another part of the solar system here in the next few years on the Europa Clipper mission for NASA. And so these are all the airborne missions that have been flown over Antarctica since the 1960s. The Coldex is just added to. If we look at a little more information than just that big gray Antarctic continent, we start to look at satellite observations of ice flow from radar satellites that can track the differential motion of the ice. You see that the ice sheet is channelized into ice streams, outlet glaciers, and all sorts of more complex processes than just that sort of gray view I gave you before. And there's another Minnesota connection here. If you see Rutherford Ice Stream here. So Bob Rutherford was actually a St. Anthony Park local here from the St. Paul campus. His dad ran the extension program back in the 1950s, and he did all of his, Bob Rutford did all of his degrees here at the U. And at the time in the 1960s, when he was studying Antarctic geology, he got to go to the Ellsworth Mountains, where the highest mountain in Antarctica is, the Vinson Massif. He got to go with support of the U.S. Army and a squadron of helicopters, map basically an entire mountain range for his PhD. And so there are a lot of Minnesota place names scattered around there, including Rutford Ice Stream, but there's also Minnesota Glacier, Gopher Glacier, Pillsbury Tower. So Minnesota has been at the forefront of Antarctic research from the early days, and certainly plenty of investigators through the decades. And I actually went back where I'll take you here in a bit, not too far from one of the first University of Minnesota camps in very remote parts of Antarctica back in the early 1960s. So always happy to talk more about those University of Minnesota connections, but sort of odd. They happen to be in the neighborhood here where I live in St. Anthony Park. Bob Rutford's house that he grew up in is 2 blocks from my house. So we should learn a little bit about Antarctic Ice Flow 101, and we can do that through looking at this most critical glacier in the world, Thwaites Glacier, which is just around 150 kilometers from where we got this ice core that I'll tell you about in a little bit. I'm just tracking time here. I don't want to get behind here. So this is both a satellite view from above of one of these outlet glaciers, how it flows onto the ocean, goes afloat, and eventually calves off these big icebergs, the sorts of icebergs that took out the Titanic, the ones that come from Greenland. Um, and if we look at this in cross-section view, I add this below. This is sort of the setup for Thwaites Glacier that we worry about for future sea level. The ocean is actually getting at the floating extension of this glacier, we call an ice shelf, and it's melting it from below due to slightly warmer ocean currents that can get underneath these ice shelves. And we're seeing through the satellite record that I'll show you um, uh, large persistent changes in ice loss from these regions that we're worried about if it moves into a region down here. I don't know if you can see my cursor. I hope you can. Um, where if the glacier retreats into this deeper and deeper inland basin, that's a runaway configuration that the glacier might not be able to stabilize. The glacier and the ice sheet might not be able to stabilize itself from. So this is sort of the basics of how the continent works, right? It's like a big bank of snow and ice. Snow falls in, it piles up, it flows under the force of its own gravity. It goes afloat on the ocean, and eventually the ocean will break off, or the ice will lose its stability and break off into icebergs. And if everything were in balance, you'd have your snow fall in, equaling your melt out. And that's not the case we find ourselves in today. And I'll show you that in just a little bit. Um, so that's a quick and dirty of how the Antarctic ice sheet works. Um, but again, I want to sort of layer under this the human component. How do we as Americans do research in Antarctica? So why do we know all of this, and why does somebody like me from Washington State or Minnesota have the capacity to go to Antarctica and still have some resources left to do science? And that's of course where our national investments to the National Science Foundation, the U.S. Antarctic Program, and our military Operation Deep Freeze, that supported our activities in Antarctica going back to the mid 1950s. So over the last 70 years, we've invested, it's hard to get a concrete number, but something on the order of 10 to $20 billion. And we've set up a system in Antarctica, including the Antarctic Treaty System that was initiated in 1961, that allows for a peaceful framework for countries to operate in this last discovered unclaimed continent. And it puts science at the forefront as a currency for leadership and maintaining peace in Antarctica. And this has been an incredibly cost-effective investment for us, especially if we think about investments that are being made in recent weeks and months around conflicts in the world. That to have, beyond just the 12 initial signatories of the treaty, but the more than a couple of dozen countries that operate in Antarctica now, all working together peacefully and just avoiding conflict on this giant continent has been incredibly useful. And we're very lucky as scientists that science sort of is the currency of this. But of course, it doesn't happen without the infrastructure of our human and physical logistics that get us to Antarctica. And that's where Operation Deep Freeze comes in, that just completed its 70th continuous year of, especially the aviation operations out of New Zealand are really critical for us to do our research from McMurdo Station, the biggest research facility in Antarctica. It's about 1,000 people in the summer. And I try to emphasize this, that our military contributions and what we do in Antarctica And all of the skills that come together in Antarctica represent people from all over the country with all sorts of skills. So, right, we have aircraft coming from Georgia and California and Washington, and the Coast Guard cutter Polar Star, our 50-year-old heavy icebreaker that was built and operates out of Seattle, Washington. Um, and our amazing icebreakers, which unfortunately we don't have anymore. They both aged out of capability, and we're a little too expensive for budgets right now. Those are built and operated out of Louisiana. So it's a big national operation that allows us to explore these fundamental questions in Antarctica. And our priority questions are around um, research that helps us understand Antarctica and its role in global systems, research that expands our fundamental knowledge of the place, and research that uses Antarctica as a laboratory for asking scientific questions that might reach beyond Antarctic science disciplines. Uh, and those questions are structured through advisory meetings and reports that come out of the National Academies of Science, Engineering, and Medicine. And so that's what identifies our priority areas. And that actually is what will lead us to seeing that sea level rise coming from Antarctica is our number one priority in U.S. Antarctic research. So our top three, though, are number three is using particularly South Pole, the South Geographic Pole, and the station that we have there to understand and observe the universe, space physics experiments, fundamental physics experiments, and understanding how the universe began using that really ideal, quiet, clean, stable atmosphere that's really great for observing some of these things. And I'll just note, we all saw some inspiring national accomplishments through the Artemis 2 mission, and I'll just note that Christina Cook, one of the astronauts on that mission, is an alumni of the U.S. Antarctic program, as a technician. She's worked through NOAA as a technician, making measurements at places not just South Pole, but American Samoa at our global monitoring stations. So astronauts tend to like to have experience in these places because they are some of the most extreme environments that we've been operating for the last 70 years. Our number two priority area is understanding how Antarctic biota evolve and adapt in the extreme and changing environments there. And then number one, my bias where my research sets is how much and how fast will Antarctica contribute to global sea level rise. So that's what I'm trying to bring ice core science to address, which really hasn't been a focus of our community, which is sort of focused on big, broad, past climate questions. And I've been trying to get us to sort of run towards this really urgent question because there are some ideal sites, in my opinion, and that we've finally gotten to in the last few years that can give us additional information that none of our sort of glaciologist colleagues can get if they're studying this glacier today. We are the only folks who can go there and drill a core and actually get detailed information about that place in the past. And that's what we've been working on. And I'll try to take you down there to do that. So let's see, just a review on our sort of situation. And let's translate this sort of physical view of how the Antarctic ice sheet works and look at our model projections of what how Antarctica might contribute to our projections of sea level rise by the end of the 21st century and actually beyond a little bit. I'll challenge us to think a little bit beyond the 21st century. And so this is sort of the overview of why that question, how much sea level rise, how fast, is our top priority in U.S. Antarctic science. So this shows our observations of sea level in the black line since 1950, and then our projections based on different scenarios of human behavior with respect to our emissions of heat trapping greenhouse gases to the end of the century that show a range of sea level rise in those lower colored lines from about a half meter of sea level rise globally at the end of the century to maybe a meter if we go into a really high-end warming scenario. But there's this pesky dashed line in all of our projections of sea level that is described here, right, as a low likelihood, high impact storyline, including ice sheet instability processes under high emissions scenarios. So, and that is referring to the West Antarctic ice sheet in that particular glacier, Thwaites Glacier. We are not sure that it won't respond faster than is ideal, particularly in the higher end warming scenarios. So again, I'll highlight that the colors here and the spread between a half meter and a meter of sea level is in large part due to our range of choices of what we do as a global society with respect to our energy systems by the end of the century. And then layer on top of that our lack of certainty and understanding of how the West Antarctic ice sheet is going to respond, and that's what pushes this upper bound that we can't really eliminate. I sort of think of it as the scenario that justifies wearing a seatbelt in your car. You wear a seatbelt because if you have a low likelihood but high impact potential storyline of getting in a head-on collision. And this is one of those things that we would really like to eliminate that from our possible futures. And so far, we've not been able to, in part because our observations of this big system that's so remote are incomplete. If we push this out forward in time, so I know that most of us are not thinking about 250 years into the future, but some of us have, Earth scientists have. And if we add from that first plot those projections to the year 2300, we get some pretty eye-popping levels of potential sea level rise. So again, in the high-end potential warming scenarios, we can't rule out something like 15 meters of global sea level rise because of our uncertainty and how fast this part of Antarctica is going to respond to that warming. So it's that uncertainty and what the ice sheet's going to do, plus our range of choices for how warm the Earth is going to be in the future. This is why we're sort of racing to understand this part of Antarctica so that we could at least eliminate these high-end sea level rise scenarios so that we don't have to incorporate them in future planning for infrastructure across the planet. Um, let's see here. I think I'm going to skip this slide here and just want to hit home here too that this is not a new thing that we've been worrying about as an earth science or an Antarctic research community. So this is just basic semantics from a paper in 1979 by scientists at the University of the Ohio State University, John Mercer, worrying about this back in 1979 in the very earliest days of our capacity to model climate with computers. And if we transition from this, he was worrying about if we doubled CO2 in the atmosphere, that West Antarctica might look like it does. And on the right-hand plot that he drew here, if we look at our observations from satellites of how Antarctica's mass has been changing, the amazing satellite missions from NASA and some of our European colleagues that track the physical mass that's being lost from Antarctica through its reduced gravitational pull on these satellites that are orbiting the planet. And they show persistent concentrated mass loss that's almost entirely in this part of Antarctica, focused on Thwaites Glacier, our critical glacier. So really key information to have that layers on that long-term sort of based on our geometric understanding of the glacier, our concern about it changing rapidly and contributing a lot of sea level. And it's because there's such a large upstream catchment for this glacier that it alone holds back something like 7 to 10 feet of global sea level rise worth of ice. And I'll just add a note here that NASA has just accomplished a lot with the space program, and the space program's budget, as requested by the president, is meant to continue. But NASA science, especially Earth science like this, looking back on our home planet, has been persistently threatened by cuts, which is limiting its ability to move forward, even if Congress doesn't actually put those cuts into place. It's really limiting our ability to understand Earth, especially at this time that it's changing. And sure, that might be in part because observing this change is inconvenient if we're pressing leaders to address that change and try to reduce it or limit the change going forward. But in any case, thinking about how we fund the science that I'm using to justify our concern about this region is really important at this time. And so this observation is not the only way we know this. For time, I'm going to move forward. And we've really come a long way in our understanding of Antarctica over the last 124 years or so. So Antarctic discovery has really progressed. So this is an image on the left there of the first Antarctic aviation, a balloon on one of the early British expeditions to Antarctica in 1902. And then U.S. naval aviation really mapped the entire coastline of Antarctica for the first time in the 1940s, and then pressing on through the 1970s, photographing and mapping meticulously the coast of Antarctica. And actually, that aerial photography archive is hosted here by the Polar Geospatial Center on campus. You can look at all of the images from all of these flight lines. And then we're in this modern era of satellite observations. But any of our airborne and satellite observations, which can more easily see large parts of the continent all at once, they need to be ground truth. They need to be tied to the ground by observation. So our ability to go to Antarctica and get these new ground observations remains critical even as our technology progresses. Okay, we've done a lot of Crash Course Antarctica 101. I'm seeing little bubbles in the chat, but I can't see it. If anybody needs to interject anything, by all means, let me know. Otherwise, we can jump through our sort of last topic and go to Antarctica here on this last expedition that I went on with our colleagues in South Korea, and I'll try to end with showing you how we're using new ice cores. Um, let's see, I've garbled my sentence there a little bit. How new ice cores can give us past climate observations near Antarctica's most critical glacier, Thwaites Glacier. Okay, so I'm going to sort of sell you on some of our limitations with this location in Antarctica. So here's this big glacier we care so much about that's changing fast. Here are all of our international research stations, year-round research stations. They're staffed through the winter, and you can see there's a conspicuous gap there. And it's not a small gap. So if we put on the approximate size of the lower 48 US states, you can fit the entire west coast of the US in this gap where we have no research stations, so we have no long-term weather or climate observations, and really limited ability to operate there because you can't just fly that far from your research station, especially given that this Pacific sector of Antarctica is really stormy, really a challenging place to operate. So it's 1,000 miles from any research station, hard to reach with no long-term observations. And I want to try, and we have gotten there to try to chip away at that problem. And our tool for doing that is these ice rises. So I've added in here outlines of all of these little mini ice sheets that are on the edge of the Antarctic ice sheet that, despite their more complex coastal location, are the types of sites that we like for ice cores. So, right, if you go back to this overview schematic diagram of a big ice sheet, we have these miniature ice sheets on the coast that are the focus of my desires and where we're going to go here. So pouring at those gives us a chance to reconstruct past climate along the least observed and fast changing Antarctic coastline. So that's why we're going through all the effort of getting there. And in this complex changing glacier system that has a lot of things pushing it around, sort of all aspects of earth science are involved in ongoing change here. Ice cores are really the one that can give us annually resolved time perspective on things that are happening at Thwaites Glacier. And if we can get there and get 150-meter deep ice cores, which is as deep as we can go in a fast mode of operation, we can get 100-year-long ice core records. And that's our limit. It snows so much at the coast. That's all we can do. And so, back in 2023, 2024, you say, great, let's hop on our US Antarctic research vessel and go there. But we have a problem in our US operations that we actually have basically no history of helicopter operations from our Antarctic research vessels, even though this one had a heli deck. And that's because helicopter operations on ships are very dangerous and expensive to maintain over long periods of time. And now we no longer even have an Antarctic research icebreaker due to the age of that vessel and the cost of it and the sort of protracted budget uncertainty at the National Science Foundation. So luckily for me, in 2022, 2023, our South Korean colleagues got wind of my interest in doing this, and they've been very capably operating their Antarctic icebreaker since around 2010. And they wanted to try their first helicopter-supported ice core camp off of this ship, which gave us a no more than 2-week window to collect the sort of ice core that I've been talking about near Thwaites Glacier. So this is our opportunity to go to Antarctica here, and I don't want to take too much longer, but I want to give you time to have a sense of what it takes to get there and what it looks like. So we went on a 60-day, 55-day cruise from New Zealand to Antarctica and back to New Zealand. And we did that so that we could get right up to these sites of interest. And so that's one of these ice rises, these mini ice sheets that we got onto as we were waiting to get off the ship with those helicopters. And we are right next to the ocean that's forcing a lot of the ongoing change in Antarctica that we're worried about for sea levels. So these sites are much more connected to the ocean and atmosphere processes that are causing the ice sheet to change currently. And so we were able to, over that incredibly long ocean journey, get right up within less than a mile, probably less than a kilometer of the site to hop over the remaining part of the ocean there. You don't want to fly over the open ocean very, very long in a helicopter, and get a lot of equipment and 8 people into this site, including 2 snow machines, so we could do ground-based surveys looking into the ice and understanding its structure. And we did that with more than a dozen flights of 2 helicopters operating simultaneously getting off the ship. So here's a little bit of what that looks like. I chose this picture on the left because Minnesotans might understand snowmobiles, given that this is part of where snowmobiles originated. But suspending this snowmobile over the ship so we could get it up to the heli deck and off the ship to our site. And this is what that quick hop off of this amazing, capable research vessel. It's actually the world-leading vessel that gets to this critical glacier. And so we, as quickly as possible, get over the not only the remaining part of the ocean, but the crevassed edges of these ice rises that make them inaccessible to anything besides helicopter. You couldn't really safely climb your way up of these without spending days doing so with much risk. Um, and so once we were able to get off and have these really clear blue sky conditions, which are hard to get in this location, we could guide in all of our equipment with these amazing helicopter pilots and our South Korean mountaineers. And with two helicopters at once, bring in all the equipment we needed. I think that's me there signaling to the pilots to bring in a load of our drilling equipment, and then establish our camp. And we actually knew we were getting into some trouble getting off of the ship. We had a storm coming, but because the weather to fly off the ship had to be just right and we had a weather window, we preferred to get off the ship into a storm rather than get stuck on the ship for 3 to 5 days. So within 5 hours of getting to the site, I would say we were preparing for bed, and this is what it looked like. Oops. Oh, you don't want to miss this here. This video is before the storm got bad, by the way. So we still had visibility. You can still see tent to tent. When we woke up the next morning, and you stepped out of a yellow tent like that, you couldn't see the next tent down the flag line. And we put those flags out as visible markers. You couldn't even see flag to flag. So we were stuck in our tents, while our larger tents got buried. So even though we were eager to rush off the ship, we knew we were going into a storm and we'd have to wait. So in Antarctic operations, we know we always are rushed to get to the next step, but we might have to wait immediately once you get to the next step of having set up your camp. And we did that. Even though our tents got crushed, we were able to sort of reestablish them and hunker down. And we spent 36 hours just weathering that storm, knowing that on the other side of that storm, once our equipment made it through, that we would be in much better conditions. And so this is what it looks like. These, any of these domes are actually more like they should be described as ice pancakes. Their edges are very steep, but their centers are very flat. And that's what we like for ice core drilling. And this is what our relatively small drill operation looks like for drilling 100 to 200 meters deep, which is as deep as we can go without upgrading to much heavier equipment. And so the drills are built, maintained, and operated by the University of Wisconsin, where the U.S. ice drilling program is supported by the National Science Foundation. A lot of polar expertise in the Midwest. We're yeah, accustomed to it, I think. That's my student Julia, who's gone on to postdoctoral research at the University of Alaska. And so yeah, this is what the setup looks like. And actually, we had black styrofoam boxes to put our ice cores in. So I'm walking through a sort of graveyard of buried boxes, all of our boxes that I buried obsessively to try to keep them as cold as possible, because black material in the sun, of course, will warm up very quickly. So that's what the operation looked like. You could tell maybe we were a little bit concerned about the wind if you look at the number of guy lines we have on that tent, but it was very secure once we got it set up. Inside the tent, this is what ice core drilling looks like, sped up. You bring up your drill meter by meter. You're drilling 1 meter at a time. You have to take out the inner part of the drill and push out the ice core there, which Julia in the back then takes and logs the length of. And in this case, because we were working with tight ship corridors and small freezers, we actually cut the cores into 50 centimeter lengths to have them in small boxes so we could move them around into the ship freezers. And yeah, once the storm's cleared, these are the most beautiful, amazing places with blowing snow and ice. You get all sorts of sun halos and arcs and sundogs in the sky. This is about as good as I've ever seen in Antarctica over the 8 or so times that I've been there. Um, so yeah, really fantastically beautiful. Always a place where we would take, if you have a minute to take to appreciate the beauty, even though we were pushing on a 13-day sprint to get our cores, just yeah, an incredible place to be. So I want to push through this so we have time for Q&A because well, I hear myself talk in my head all the time. We could immediately start seeing climate information in the cores. Antarctic ice cores, you actually can't see that much, but when you're on the coast, where it does occasionally get near freezing or above freezing, you can see these clear lines in the cores, which are melt layers, which are a really clear physical indicator of relatively warm temperatures at the site that go into our estimations of past climate conditions. So this is a really interesting project for us because typically through the U.S. Antarctic program, we have about 3 months of sort of plodding, steady progress to get our coring done, to get out to our field sites. This was much more of a slow ocean journey and then a rapid hop off the ship and have a 13-day sprint to set up our drill equipment, collect these cores, and through this U.S. drilling equipment and an identical operation from our South Korean counterparts, we actually collected two identical cores, which is really good for our reproducibility and understanding how the site preserves climate information. We got those as soon as we hit our 150-meter target, and the ship was able to come back and pick us up. As soon as you're done drilling, it's then pack up your cores, get them into cargo nets, and ready to sling them back to the ship. And again, this is the first helicopter and icebreaker supported ice core project in Antarctica, basically, and just an incredible operation that really only South Korea can accomplish right now. Again, in partnership with us, if we bring our U.S. drilling equipment and some of the support from the U.S. National Science Foundation. So, um, yeah, I really can't convey to you how much of a dream project this was to get done. My colleagues in South Korea have become fantastic friends and colleagues, and we continue to work on the cores. But yeah, it was just a really proud accomplishment from this small team that went through a lot. We're really patient on the ship and worked really diligently, made very few mistakes to get all these things safely accomplished. And these were our hero shots after we finished our coring, but our preferred sort of family favorite was us with our collapsed tent that we continued to use for that 13 days after the storm we experienced. So, I thought it was really refreshing to see again, the NASA Artemis astronauts as they came back and described the experience of those four people going through such an intense 10-day experience. I wouldn't at all equate what we're doing to flying around the moon, but we have similar experiences like that in Antarctica, where it's only these 8 people that understand the hardships that we went through and the mission that we were all dedicated to in collecting these cores, given what we knew they could tell us about this critical glacier. And so it's so gratifying to get something like that done. And further gratifying is actually getting some recognition when you come back home. We worked with a science journalist all through the journey to get it featured in Science Magazine, and I don't think I'll ever get a better byline here or headline: "Daring James Bond Mission to Drill Antarctic Ice Cores." That mode of hopping off and rapidly collecting these ice cores from a ship is quite unique in the way that we operate in Antarctica. So I don't have a lot of results to show you from the cores yet because it's still in progress. I did get to go to South Korea and test out their clean room fashion last summer, and hopefully we'll go back again this summer. They've been working on the chemical analysis of the cores, which is the first time they've ever done this with an ice core. So our work has really motivated them to increase their capability in ice core science, which is really exciting. And I'll show you the first results as we fly from the site back to the ship here. So, right, there's a lot to go through actually, this was even a slightly aggressive line here. We've only got 100 years of climate information from this site through all of this effort, and it's all we can really get in the mode of logistics that we have there, these helicopters and icebreakers. But it's 100 more years of perspective than we have ever had on this glacier due to its remote location. And we have the first chemistry coming out of our South Korean colleagues. So this is looking at the annual variability, or the variability with depth. 0 meters is on the left, 100 meters is on the right, of hydrogen peroxide, which is only produced in the summertime in the Antarctic atmosphere when the lights come on, right? It's light for 6 months out of the year. And that makes a big, clear summer marker. And so we count all of those back. And at 100 meters depth there, we still have 50 meters left that they haven't analyzed. 100 meters depth is the year 1966. And the spacing, the distance between each of those summer peaks is the amount of snow that fell this year. So we can convert that once we count each of those peaks, we can convert it into a record of annual snowfall rates. And the amount of snowfall that comes to a place, as we know in Minnesota, is controlled by the broader patterns of motion in the atmosphere. And we can use that to understand how the atmosphere has varied in the past. Over this time period, we have other satellite observations and model understanding of how the Antarctic weather and climate has progressed. But as we finish the lower part of this core, it's going to push back to the year 1920, and we'll have a record of not only the variation in snowfall, but estimates of temperature, estimates of sea ice conditions, wind conditions, all sorts of things that contribute to that, right? Gaining this additional perspective in a place and in a time that we have really wanted to have observations so that we can understand the sensitivity of that system, that Thwaites Glacier system, today and in the last 100 years, so that we can think about how it's going to be behaving going forward and potentially contributing to sea level rise. So I think I've hit most of my mission here. So we've gone over some Antarctica and Antarctic Ice Cores 101. You've learned about West Antarctica and why it's concerning us so much with respect to global sea level rise in the future. And then we went to Antarctica very quickly, looking at these new ice cores that we collected back in 2024 that we're continuing to work on. And I'll just emphasize again that broader point, right? Americans do Antarctic research with support from the National Science Foundation. And that research is done then in university communities across all job functions all across the country. So if you think this work is valuable, hopefully I've convinced you of a small bit of that. I'd encourage you to support sustained funding levels at the National Science Foundation um, to allow folks all across the country to apply their best thinking to these critical problems. We're in a really challenging situation with the budget requests that are coming out each year. I didn't even update this slide from the 2026 to the 2027 request, but the White House budget requests are for historic cuts to science funding across NSF and NASA that are really without precedent. And already just the requests have led to a major stalling in sort of the engine of science and research and development in this country. So I'm happy to talk more about that in the Q&A. I don't want to take any more time. I really thank you guys for your attention. And if you want to follow along, I share more about this on social media than most professors, certainly. So you can follow me on Instagram or TikTok. I know all of you lifelong learners are on TikTok, so that's no worries there. But also our Cold-X Science and Technology Center is on Instagram. And thanks to our great digital communicator here at the University of Minnesota, Martin Froger, he's also on Instagram and has shared a lot about this great work. So thank you all so much, and I look forward to the Q&A.
All right, thank you so much. This is just fascinating. I think all of our participants today have really enjoyed hearing about this and seeing these amazing videos. I just start maybe with a very, very basic question that a lot of people are asking, which is just what is it like to live and work on this massive frozen ice sheet in a small
Yeah.
space with people that, maybe don't all speak your language, but what is it like to live there and work there?
Yeah, I mean the language and cultural difference with the South Koreans was an incredible new addition for me. And that, I mean, I think it was my eighth time being to Antarctica, but it made it entirely different. Like I was all new again, being on a ship. I'd never been at sea. Thankfully, I don't get seasick, so that's my superpower. Um, but yeah, amazing experiences that are akin to that we call it deploying to Antarctica, like being on a military deployment. I mean, you're in these really intense situations where you're facing this big powerful continent that is always challenging, even our most advanced capabilities in aviation, which has really, advanced our capability to operate in Antarctica. But you have to stay humble, and you're working with, yeah, small groups of people in really intimate situations, needing to keep each other safe and healthy and happy across all the, science and life functions that one needs to survive down there. So it's like the most overwhelming and gratifying experience that I can imagine. And I think of, that a Canadian astronaut, Jeremy Hansen, when he got back from the Artemis mission, his first summaries, and I won't be able to quote him exactly, were sort of right on the mark of like, that people see themselves in people who do sort of hard focused work. And I've had that feeling in the Antarctic program, and we don't get to express it publicly like NASA so ably enables our astronauts to. So again, I'm not likening us to astronauts, but yeah, it's overwhelming, and that sense of accomplishment through, the collaboration that it requires across, people who fly planes, people who repair equipment, people who drive heavy equipment and repair equipment and fuel your aircraft and run the accommodations at McMurdo Station. Like everybody is contributing to this mission. And I wish we had more of that across American life. And that's why my view of public service and what we do with our federal investments, the ones I've interacted with, it's just such an amazing shared mission that yeah, I wish we all had those experiences. So, and
Yeah,
I haven't even talked about penguins yet, right? But that's also a nice bonus.
yeah, I can't wait to hear about the penguins. But yeah, it does sound life-changing. And clearly, you and these very limited few other people have gone through things that no one else really will ever experience. And I think that kind of gives me goosebumps just to think about. So that's awesome. Okay, why South Korea? Why is South Korea so active in Antarctic research?
Yeah, that's a great question. They are an ocean-focused country that a lot of their food, their proteins come from the ocean. So That's sort of a core part of it on their national motivations, but they're also, one of the most rapidly that country rapidly developed in the, latter part of the 20th century, in large part due to key partnership with the United States, after the Korean War. Um, and polar operations and doing polar science is sort of seen in international affairs and geopolitics as a really high-end accomplishment of any nation. So it sort of gives you um, that presence on the global leadership, and being a very active scientific party that's doing meaningful work in the Antarctic Treaty System. It sort of elevates their national geopolitical standing, I think, is a part of it. And they also, from the ship perspective, I mean, they're some of the world's best shipbuilders. Hyundai Heavy Industries is really contributing to trying to reinvigorate the U.S. shipbuilding industry. So, um, yeah, and I don't know why they've been so committed to having helicopters on their ship, but they have, and they're now the world leaders in this type of research, and especially access to Thwaites Glacier. I see in the comments here, Paul Berman said he enjoyed the PBS NewsHour special from Miles O'Brien, and Miles was on the RV Aran on its return to Thwaites Glacier after the last time we were there. They're going now every other year to this site, and they very smartly, right, talk about national profile. They had a New York Times journalist and photographer, and they had Miles O'Brien and his producer. So they had coverage across CNN, PBS NewsHour, and New York Times. And the New York Times last article about it was, why is South Korea here? And why is the United States not? And it's because we've lost focus on our funding for our science agencies, and on our ship side of things, our ships were both of our last icebreakers, the NSF icebreaker and the latest Coast Guard icebreaker were built in the 1990s. And that industry, icebreaker shipbuilding is very specialized for the sort of thick hulls and particular material you need to make those strong ships that can deal with those conditions. We're just sort of we're behind. And it sort of connects to our, I think, as a nation, being behind on a lot of our physical and human infrastructure over the last few decades.
Yeah. Okay. Um, so I think these two questions I think are basically the same. I'm gonna let you figure that part out, but um, what causes this approximately 100,000 year cycle of warming and cooling? And is this the wobble cycle of the planet's orbit or not?
It's always all of the above, but it's not only the wobble. It's not only our the obliquity of our orbit around the sun. I got my sun Lego model here, which is my thing to hammer home with my intro weather and climate students. So I teach right
Uh-huh.
now that our relationship to the sun is everything. It's so crucial. It's so amazing. It's that, I guess I should probably worship the sun. If I worshiped anything, it'd be worshiping the sun. But yeah, right. Due to the 100,000 year cycle and how round or oblate our orbit around the sun is, that really controls the amount of sunlight that's hitting Earth's surface at key latitudes that affect, based on the land, where the land surfaces are on Earth, that affect how you can build or melt an ice sheet. So that's really the big one. But layered in are, yeah, slight variations in the angle of our tilt axis, right? We're at 23.5 degrees now, but that can be 24 degrees or 22 degrees over 40,000 year timescales. And then also there's sort of a precession, a spinning of the top that happens on 19,000 year cycles. And so those cycles all filter on top of each other. And that's part of having these long ice core records of temperature estimates and direct observations of CO2 from those air bubbles in the ice that allow us to check our understanding mathematically, right? I mean, it's somebody in the 1930s and 40s, this guy Milankovitch, who calculated the physics of all of the different objects orbiting the sun, and it's those, right? It's because we're not the only object in the solar system that our or orbit around the sun is sort of tugged on by the other massive bodies in the solar system. So yeah, it's amazing, the all of the different factors that are at play in this. And if we weren't adding greenhouse gas into the atmosphere right now, we'd otherwise be cooling due to those orbital forces alone. And those all go into our big, our model understandings of where we are today and where we're headed for global temperature.
Wow. Wow. Okay. So given what we just talked about with the wobble and the orbiting and all of that. So the Earth is not completely round, is that right? So in other words,
Sure.
if the glaciers really started melting fast, would the sea level rise be the same at all points around the globe?
Yeah, it would not. Another really cool effect, right? The Antarctic ice sheet and the Greenland ice sheet are such uh, uh, geographically, what am I trying to say? They're big accumulations of mass on Earth, and so they have their own gravitational attraction that where they're pulling the ocean because of that material is less viscous than ice or rock. It can pull itself, pull the ocean towards it, sort of like pulling a blanket towards it. And as the ice sheet melts and sends its mass distributed over the ocean, its ability to pull on the ocean becomes slightly less. And so that actually means that there's sort of some karma in here. I feel like that far field sea level rise, far from the source of your glacier melting, far from Antarctica, say North America, we actually get extra sea level rise because we're further from that ice sheet contribution to global sea level rise. And just for reference, about half of our sea level rise right now is just from warming of the ocean and it expanding volumetrically, which would happen, it happens to your pot of water as you boil it at home. That's half of the sea level rise we see right now. And the other half is actually mostly from mountain glaciers melting right now because they're so much smaller. They have less thermal mass, so they respond more quickly to a globally averaged warming. And then Greenland is coming behind mountain glaciers, and Antarctica is catching up.
Ah, okay. So maybe you had addressed this earlier, but why isn't the Arctic as good of a place to do these ice cores as the Antarctic?
Yeah, that's some really cool, just fundamental Earth system stuff too, right? Like think of where the most land area is on Earth, Northern Hemisphere or Southern Hemisphere. I mean, the Southern Hemisphere is basically an ocean hemisphere, and the Northern Hemisphere has something like 75% of the Earth's land area. That might 75%, it might be a little high. Um, so that means from the Greenland ice sheet perspective, as a place to preserve air trapped in air bubbles, it's sitting in an atmosphere that has something like 20 times more dust in the atmosphere than the southern hemisphere. And that dust
Hmm.
gets deposited on the ice sheet along with the snow. And dust, has various mineral compositions, but it can have some calcium components to it and minerals that can activate a little bit of biology in the snow and ice. And
Hmm.
that alters the CO2 concentration. So, of course, it took some figuring out to understand why back in the 1980s and 90s, why the CO2 records from Greenland ice cores weren't making sense. And that was it. And so the methane in greenhouse or in ice bubbles in Greenland ice cores is not affected by that. So we have great Greenland methane records, which is really convenient. So methane or CO2, they're globally well mixed gases on a couple month time scale. So the methane records from Greenland can be correlated directly to the methane measurements from Antarctica. And so it allows us to date the cores uh, to align the dating very precisely, which can also tell us how the southern hemisphere transmits warmth from southern hemisphere to north and vice versa, and whether or not warming on Earth is transmitted through the atmosphere or if it's transmitted through the ocean, just based on the amount of time that it takes to move heat through those systems. So yeah, really
Hmm.
good question. It's if one of those like I mean I it's probably make it as an unfortunate quiz questions for my students. Why is Antarctica the only place where we can reconstruct past CO2? And it's because the ice is so clean.
Yeah, that's fascinating.
Great,
Okay,
great drinking water when we're down there too. Very clean.
I do you yeah, do you just drink what you melt?
Yeah, sometimes some projects where we're like melting large volumes of ice to get large air samples to study, we literally will take a hose into our camp water jugs. I mean, yeah, it's my mom's a nurse and she always worries about bacteria and ancient viruses in the ice and like clearly we have enough trouble with that in the modern era. It's not us releasing viruses from the Antarctic ice, but so far so good. But there's so little life in Antarctica. As soon as you go 5, 10 miles inland, I mean, there's no possibility, even if birds, and we do get birds flying sort of further into the ice sheet occasionally. I've seen a couple of times, but there's so little life when you move in from the coast there.
You're just drinking future scientists' ability to understand
That's true.
2026, right?
That's true.
Like,
Yeah, we do probably leave some odd evidence too in some of our projects where we leave leave past boreholes, or sometimes we throw ice that we don't use for science. We throw it at the bottom of these boreholes, and that'll, yeah, put things out of order
Oh
sometimes.
no. Yeah. Okay.
Very rarely.
Okay. Well, so someone is asking, while the edges of, I believe they're referring to our Antarctica, are being lost due to warming from the sea below, what is the effect on the regions far from the oceans? I'm assuming the very center of
Yeah.
Antarctica.
Yeah. Antarctic climate is really variable, and we've only been observing it for 50, 60, 70 years at a few places. So it's a really noisy climate with a short observational period, which is really, really bad if you're trying to detect change. Detecting a signal change in a noisy system is you got to wait a long time to get some statistical significance. So the continent writ large is warming. The warming is still subtle with respect to how variable the climate is. One thing that you might hear is that some of the mass loss that we're seeing in West Antarctica from this coastline that I study is that it's being made up for in additional snowfall across much of the rest of Antarctica. And that is true in the last year or two. There's been some massive snowfall events. There's actually the most extreme heat wave ever observed on Earth happened in March of 2022 across that rest of East Antarctica, where it was a almost a 40 degrees Celsius warm departure as it was supposed to be falling off into the winter. They had a massive warmth, and with that was a big marine air push onto the continent, and it brought with it, I mean, trillions of kilograms of additional snowfall. And so that process is happening simultaneously to this ice loss still happening in West Antarctica. So my way of thinking of that is there are processes. I mean, if we warm the atmosphere, warm air holds more moisture. That's why it's been so warm here lately and why we're having thunderstorms right about now as we're transitioning from warm to cold air. But that warm air, we expect that there should be some additional snowfall in a warming world that can offset some of the sea level rise. And so we are seeing what we're seeing is in line with those observations. And my sort of lay explanation for that is like, imagine if you're going to a used car lot and buying a used car and you see that like, oh, okay, that, it's leaking oil. Like that's a pretty big fundamental problem. Um, but your used car salesman is like slapped a new coat of paint on it. He's like, oh yeah, look at this. We got a new coat of paint. So it's sort of superficially, it looks great. That new snowfall is sort of like slapping a new coat of paint on the ice sheet, but it's still leaking oil out of this Thwaites Glacier. You have this sort of fundamental problem structurally at that glacier, and we're not seeing that process let up at all. Um,
Mm,
so,
mm.
you can walk and chew gum at the same time. Two things can be happening in opposition at the same time, and our understanding can still be relatively complete. But, people will run away with that headline of, oh, the snow, it's making up for everything.
Yeah.
I wish it were true.
Yeah. So speaking of that Thwaites Glacier, is there any chance that that whole thing can just go at once?
No, and that's part of the challenge of communicating about this. People often talk about that in the press, they've called it the Doomsday Glacier, which gets a lot of attention. And we talk about collapse, ice sheet collapse. Any collapse, ice shelves, the floating part of that glacier can collapse. And actually, it's showing signs that in the next months to years, it will lose its floating part of that glacier, which is already a pretty mangled, messy jumble of basically a bunch of icebergs that are barely held together right now. But the inland part of the ice, which, steps back and gets thicker and thicker and thicker up to it being, a mile and a half or 2 miles thick, that changing will take, years, decades, centuries. But we are worried that it can, we're worried that we see physically that it could behave on the faster end of our expectations. And that, what we're basically trying to figure out how we could eliminate that possibility. And anybody who finds the result that really convinces, a bunch of scientists who study this so that like, yeah, wow, okay, we really can eliminate that top end scenario. I mean, obviously that's a pretty high bar um, to convince folks of, and it's not really something we expect to be able to fully eliminate. But we're trying to gather evidence to give us confidence, for folks in the Netherlands who are trying to build coastal infrastructure, anybody across the coastal US, right? We rely on coastal infrastructure for everything in our global economy. So us being in Minnesota doesn't mean we don't have to worry about sea level rise. Obviously, we worry about, river levels in the Mississippi River and flowing down the Mississippi to markets in Louisiana and beyond is critical to our state economy too. So nobody's sort of outside of this. And everybody, if you need to make changes to your coastal infrastructure, you want to have the best information and you want to be building your infrastructure for decades into the future, not just to be rebuilt every 5, 10 years, right? We want to save expense. We want to avoid risk. We want to protect people and livelihoods and our infrastructure. And so we're trying to get that information, um, whether or not folks are really asking for it at the moment too. I mean, it's just such a challenging time right now where at the federal level, folks have are trying to avoid dealing with this big pesky problem of observed warming and knowing what's causing it and knowing that our global energy systems are really the central cause of warming. We know all of that, and people, there's really not much getting around that anymore besides just trying to avoid meaningfully dealing with it and or dealing with it in a way beyond how the markets will deal with it eventually.
Hmm. Okay, on these research trips that you've been on, well, first of all, how many times have you been to Antarctica?
Yeah, I think I've been saying 8. It a little bit depends on how you count, but I've been
Oh,
on one, I've been on 2 NASA airborne survey missions, actually over Thwaites Glacier. So about a decade ago, I got within 1,000 feet of this place actually that we drilled in this big critical glacier on some NASA survey missions. But 7 or 8 times. I actually went twice the last season. Our season to operate down there during the summer is sort of November through February. And I actually went
yeah.
down to one part of Antarctica for all of November for the Cold X project. And I came home for 2 weeks. And then I went and caught the South Korean icebreaker in New Zealand, I think on Christmas Day, actually,
Ugh.
and was on that for another 2 months. So,
So on any of your trips, have there also been any life sciences researchers or just geologists and glaciologists?
yeah, if we're operating through the US program and working on ice core projects, those are sort of self-contained and they require enough support that we are the focus of the resources we get. We interact with other scientists when we're at McMurdo Station, which has a large lab facility um, that has those biological researchers, the SEAL, of course, they call them the SEAL team who study
Hmm.
seals there. Folks who dive under the water there. We have a diver in our Antarctic program who's the most accomplished polar diver in the world. And you get to see the results of that stuff. They have a live touch tank in the McMurdo Science Lab where they bring in the critters from the water there, and folks can go on the weekends and interact with them, including right people across the station, not just scientists. So, um, and then yeah, on the icebreaker, right, working on Antarctic cruises or oceanographic cruises of any kind, you have to maximize that ship time as much as possible. So, there are different focuses across the disciplines, and so I mean, right, we're ice core people are sort of like the Marines on the ship waiting to deploy when you get to your site of interest. But folks who are studying the ocean are ready 24/7 to, if they get to a location where they need to repeat an observation of temperature, salinity, that sort of thing, they'll do that. And they'll do it around the clock when we're otherwise operating with other science in mind. So there's a diverse suite of science for sure on research vessels.
Okay, switching focus just a little bit, we have a couple of questions about tourism. Specifically, what do you think of the role of tourism in Antarctica or the impact that it's having? And do you know if there are limits still being placed on it?
Yeah, absolutely. So, like all human activities in Antarctica, tourism is managed under the Antarctic Treaty System and through an international consortium of operators. It's called IATO. I can't remember the exact acronym. So, yeah, I certainly have mixed feelings about it. I have mixed feelings and I'm apprehensive that actually I'm the host for a group of university alumni that are going on one of those tourist cruises to the Antarctic Peninsula next January. I view that as a really interesting sort of long format experiential learning opportunity where especially I can get out my kicks. I can talk about Antarctica for 2 weeks rather than just for an hour with you all. Well, and I do this to my grad students every day, but uh, yeah, the numbers for tourism growth are really quite eye-popping, right? In the 1990s, mid 90s, then it was like 4 or 5,000 people a year were getting down there on ships from southern South America, largely to the Antarctic Peninsula, which is where there's, right, it's the furthest north part of Antarctica. It's warmer. There's a lot of life. It's beautiful. There are mountains and glaciers. And since COVID, the numbers have pushed above 100,000 people per year. And that obviously has an impact on that smaller portion of Antarctica, which is the fastest changing, fastest warming part of Antarctica as well. There are direct impacts, on the concentrations of soot emissions from these ships and concentrated human impact on the historic sites and beaches and things that are frequently landed at. And that can be an opportunity, if you focus the impact on a few places, sort of cost benefits there. I'm not a conservation scientist, but yeah, it's really a challenge, and it also serves a particular demographic, right? Obviously, going to Antarctica on a tourist ship is not something that's accessible to everybody. Um, and so that also affects, who's seeing this place. I think the most idealistic hope is that people seeing the place and experiencing it, there's no better way to understand its global importance and just how extraordinary of an environment it is and worth preserving. Um, but then what those folks actually do then back in their normal life to advocate for the place or support research funding or whatever different priorities they take out of it is I think harder to quantify what people do after the fact. And I do know as well, and I don't think I contribute to this, and I aim not to, but social media also, Antarctica is one of those exotic locations that has increasingly become a place where online content creators take themselves just so that they can get drive traffic based on that exotic location. I benefited from that in my science communication, right? Having Antarctica to show folks when you're talking about that type of science is really a useful hook for us to talk about our research. But yeah, it's you know any of our activities conveying ourselves all across the world, especially if it's for recreational purposes, is increasingly right? It's very high impact with respect to the carbon that it emits, and same as our research, to not at all come across as hypocritical, right? Being on a diesel consuming icebreaker for 2 months, flying helicopters consuming jet fuel. I mean, you can look up a picture of McMurdo Station, and the first thing you'll see are giant tanks of diesel all across the station. The entire program operates on diesel and jet fuel, so that's a
Hmm.
major challenge of operating in the polar extremes and thinking of the changing Arctic as well. Everybody's getting excited about less sea ice and more potential for shipping through the Arctic. It's a really energy intensive place to be, the polar regions, and energy intensive is not what we need to be thinking about long term.
Yes, true. So along with tourism, there's a question about the population growth of the world, and is this contributing, in your opinion, to climate change?
Yeah, it certainly is, but it's not the main cause of climate change. It's one of the things that folks like to throw up as a distraction in the actual cause of warming, which is burning fossil fuels and that adding to the greenhouse layer in the atmosphere, which again is great. We need the greenhouse layer. We'd be like the moon if we didn't have the greenhouse gases we have in the atmosphere. And we're now just adding more beyond what we've had as we developed as a civilization over the last 10,000 years. Um, but right, there's sort of like chicken and eggs here, where it's like, human development, getting into the industrial era, industrializing through, early sources of hydrocarbon fuels, coal, things like that, and then finding oil as our energy source that we're currently um, primarily using. The use of those fuels has been biased towards more developed countries. So population growth hasn't necessarily been in those developed countries like the United States, which is still over time the largest historic emitter of greenhouse gases. So that source of energy has contributed to our prosperity in the United States, which has then also through are investing some of that prosperity back into research and development, which I'm sitting in Borlaug Hall, named after Norman Borlaug, who won a Nobel Prize for spreading the Green Revolution across developing countries like India and other Southeast Asian countries, right? That allowed then population growth in those countries to, move towards their own development that we enjoyed as we discovered hydrocarbons as a fuel. So there's a lot of complex issues in there, and I'm not an expert in all of them, but you always have to think most broadly, not only about one set of numbers, population growth, but certainly, right, people love that exponential increase in greenhouse gases, exponential increase in prosperity, exponential increase in population. Like obviously a lot has happened in the industrial era, but it doesn't come without challenging repercussions. And now, right,
Yes.
as we try as a global society to regulate emissions of greenhouse gases, you have issues then of fairness for developed countries trying to reduce their emissions, but developing countries then needing to deal with why should they be handicapped in their development, unlike we were when we developed without any regulations on that source of energy.
Okay, I think that we probably have time for one last question, and this is a great question to end on. What is your favorite personal and also historic global ice core discovery?
Whoa. Um, that's tough. I mean, I'm always struck by the just the beauty of having glaciers recording information that, as a place we can go to as we realize we need to understand some of these processes and how they interact with changes we're imparting on the Earth system. But I think of like the records that some of our colleagues produce that I have the pleasure of working with now out of Australia, where they have a site that's produced our highest quality records of the industrial era increase in greenhouse gases. I think you can see some of them behind me of the blue, let's see, which one is it there? The red one on top is you can't even barely see it there, but stable levels of CO2 before humans industrialized, and then that
Mm.
industrial increase. Just such a direct, clear, well done piece of science. And yeah, I have the pleasure of working with these people. Guy Dave Etheridge, who's just now retiring from one of their national scientific research agencies. But I got to go back to this site in Antarctica with him. The first time he went there, not to date him or myself, but was the year that I was born. And we got to go back there together, on his likely last time there, and to do sort of the next round of science on that archive that showed us how the atmosphere changed, and then he demonstrated how clean of an archive that is. And we actually went back in 2018, and we're working on publishing the results now. Science does not always happen fast. About 10
Mhm.
years from a project being designed and proposed to us writing it up for Nature magazine this year. But we went back to that site to reconstruct as we've changed the atmosphere in that exponential way. We can measure a really small part of the atmosphere that actually controls the lifetime of methane in the atmosphere, something that oxidizes methane out of the atmosphere and sort of cleans the atmosphere. We really want that to have been keeping up with the cleaning over the industrial period. And we were able to do really, really, really tedious, hard work to reconstruct that. And so we have the first record of that oxidizing process over the industrial area. And then it's a good news story. We worked for 10 years to get a flat line. And it shows that the atmosphere has kept up with its housekeeping, even though we've massively changed the chemical composition in some ways. So that's, I don't
Interesting.
know, my long-winded answer, but
No,
to
no, that
see
was a
that
good
beautiful
one.
data set and then work with the people that produced it, it's yeah, been a really cool experience.
And
And
you have
yeah,
decades more of interesting discoveries ahead of you.
I hope so. Yeah.
Yeah.
Trying to hang in there, and it
Yeah.
always comes and goes. And we all have a lot of things going on and challenges to deal with as a nation and as a global society right now. So yeah, we've all got to focus on our area, and I'm trying to make Antarctica mine as much as possible. And we're all being encouraged to sort of diversify our focuses right now, trying to
Hmm.
keep my eye focused on Antarctica because I think it's a really, really important place where the United States has led for the last 70 years. And we need to continue to do so because peace is sort of the ultimate thing that we get out of doing that. And uh, yeah, I hope we can all agree that's a pretty high value item to try to pursue.
It's a lovely place to end that sentiment. Thank you so much. So thank you, Dr. Neff. The audience, as always, I'm always grateful for your questions, and I'm always sorry that I don't have time to ask all of them. Thank you to the OLLI program and our sponsor, the University of Minnesota Alumni Association. Please join us next week on April 30th for our next presentation, which is called How Your Favorite Childhood Stories Came to Life with Dr. Lisa Von Drasik. And we'll see you then. Thank you so much. Bye.
Yeah, thank you all. You can follow on social media if you want to learn more.
Thank you.